So up until now, we've either derived a function or been given a function, and we constructed a table of values in order to find points to plot on a graph, and therefore we were able to sketch the graph of a function. Well, now we're actually going to go in the other direction. We're going to be given the sketch of the graph of a function, and we want to take out a few points on this graph to construct a table and go in the other direction and actually find the function that is described in this graph. So let's go ahead and do this. Let's pick out a few points on this particular graph of a function. Well, we know one right off the bat is the origin. This function goes right through the origin. So we have the point 0, 0. Let's pick another one. We have one right here we have 1 and minus 1. 1 and minus 1. Let's pick out some more. We have another point at 2 and minus 2. We have another point at, let's go in the other direction, minus 1, minus 1. So minus 1 and minus 1. And let's get one more. We have another point at minus 2 and minus 2. Okay, so let's go ahead and construct a table using these points. So we have our x and our f of x. Alright, so we have 0, 0. We have 1 and minus 1. We have 2 and minus 2. We have minus 1 and minus 1. We have minus 2 and minus 2. So we want to use this table of values to actually to derive the function that was graphed over here. So what can we say about the relationships between the domain and the range? So if we want to write our function f of x, we need a general pattern, if you will, of the relationship between x and f of x. Well, it looks like we both have the same number. They're both 0, 0, 1, 1, 2, 2, 1, 1, 2, 2. So it's going to involve some term x that we're going to either take a negative of or do something with. Well, we can't just say f of x equals minus x, because it might work here. If we plug in 1 into minus x, we'd get a minus 1. If we plug in 2 into minus x, we get minus 2. But look what happens with the negative numbers right here. We plug in minus 1 into minus x, we'd get a positive 1. And right here we have a minus 1. So minus x isn't going to do it. But I argue, how about this? We put absolute value bars around the x with the minus on the outside. What that's going to do is whatever number that we put in here, either positive or negative, we're going to get the same number with a minus sign, and that's actually what we have here. So we can just plug in a few numbers to make sure we're right. If we plug in 1 here, we get a positive 1, so a minus positive 1, which is right here. Let's go ahead and try the other one. We have minus 1. Let's plug it in for x. So we have the absolute value, the opposite of the absolute value of minus 1. Well, that'll just turn this into a 1 with the minus sign out in front, and that's actually what we have here. So this looks like a pretty good function that describes the function graphed here. Okay, not a whole lot to it. We just need to use a little bit of intuition. Sometimes we need to think outside the box, but it's nothing that we're not able to handle at this point. So let's take a look at the next one. We are given the graph. This is the f of x axis. F of x, this is the x-axis, and this is all we're going to need here. Let's say we're given the graph of the line, the horizontal line running through f of x equals 2. So we have a horizontal line here running through f of x equals 2. Okay, and it keeps going in both directions indefinitely, and we want to derive the function that describes this horizontal line. Well, after seeing working with horizontal lines in the previous sections, we should be pretty familiar with this, but let's go ahead and do the math on it. So we need to construct a table of values. So we have our domain and our range. So let's go ahead and construct a table of values. 2, 3, 4. So we need, let's go ahead and pick some points. So we have a point right here at 0 and 2. We have another point right here at 1 and 2. And let's go in the other direction. We have a point right here at -1 and 2, and let's write out one more. We have -2 and 2, and just go ahead and throw in, we have 2 and 2 right here. Okay, so it seems like no matter what we plug in for our function f of x, we're gonna get 2 as the output. Well, that's actually all there is to it. Our function f of x, no matter what input we use, no matter what value we have for x, this function is always going to equal 2 because it's horizontal, it doesn't have any slope, so our f of x equals 2. This is our function. So we can plug in any value for x and it's going to spit out 2 every time. So this was actually pretty simple. There wasn't much to it at all. We just need to think about what we know about what a horizontal line does, what its attributes are. And we know that it will never leave f of x equals 2 if it's truly a horizontal line with no slope. So f of x equals 2 describes our function that's graphed here. All right, let's do a couple more. Let's look at the next one. This function is going to be graphed solely in the first two quadrants. This is our axis f of x, and this is our x-axis. All right, let's scale this thing. Okay, so our function looks something like this. We have the function passes through 1, 1. Does something like this. And it does it in both directions. Okay, that wasn't terribly straight, but you get the idea. Okay, so we want to know what the function of this graph is. So let's go ahead and pick out a few points and put them in our table of values. So we have the list of our domain values and the list of our range values. We want to pick out at least 3 or 4. So we got one right here. We have our function goes through the origin. We have a point right here at +1, +1. We have another point right here. This point is at 2 and 4. 2 and 4. Let's go ahead and grab a couple more on the negative side. We have -1 and 1. And over here, kind of looks like a mirror, we have -2 and 4. -2 and 4. Okay, so this is our table of values, and what we can actually quickly pick off is that notice that the function squares the input values. 2 times 4, or 2 times 2 is 4, so 2 squared equals 4, but we also see the same thing with -2. If we squared -2, that would also give us 4. If we squared -1, that would give us a +1. If we squared +1, we'd get 1. So the function here is actually a very popular function. It's used quite extensively, and this function is f of x equals x squared. Okay, this function, be sure you get very familiar with it because we'll actually use it extensively when actually you get up into calculus, and it just makes a U shape and it oscillates, or its vertex is right at the origin, and it actually is symmetrical. This side is identical to this side, even though you can't tell because I can't draw very well. So very important. It's called x squared, and it's a very important function. So let's make room for one more. Okay, here we go. Let's take a look at the following. We have the following graph, and this is just going to be a rough sketch. We have the graph. This is going to describe the real-world situation of driving the distance driven by a car. So this is our f of x, and this is our x-axis. And we have the following values for f of x. Our scale is going to be 60, so we're going up by 60s. Scale is very important when either you're graphing functions or you're interpreting the graph of a function. But f of x is the dependent variable, and it's described as distance, and it's going to be in miles. In miles. That says miles. Sorry about that. Okay, so this describes our distance in miles, and our x-axis, or our independent variable, is going to describe our time, our driving time, in hours. So we have 1, 2, 3, 4. And we're given the graph. It's going to look something like this. Let's get a different color. There we go. And this continues on infinitely in this direction. Okay, so the graph shows a distance driven by a car. What we want to do is we want to find the function representing the distance as a function of time. Okay, so let's go ahead and make a table of values using a few points from this graph. So we have x and f of x. Okay, well actually let's go ahead and change our variable since we're dealing with time here. We want to write our distance as a function of time, so our independent variable is going to be t for time, and our dependent variable, which is distance, is going to be f of t, which is going to be a function of time. I just want to show you that we can use different variables and everything will work out the same. So we have a point right here at 0, 0. At time 0, we've gone 0 miles. We have another point right here. So after 1 hour, we've gone 60 miles. We've got a point right here. After 2 hours, we've gone 120 miles. And you can tell that this is indeed a linear function. After 3 hours, we've gone 180 miles. And after 4 hours, we've gone 240 miles. Okay, that's it right there. So 240. So we can see that for every hour the car travels 60 miles. So we know that distance equals 60 times time. Okay, it's going at a rate of 60 miles an hour. So we can write, and we saw this a few times when we were graphing linear equations. So we can write our function f of t. Remember, f of t is our distance. This is t, and this is t. F of t is our distance. It's our dependent variable. So it's going to take the same form of this distance formula, but it's going to be f of t equals 60t. So 60 times t. So our distance is dependent on the number of hours that we drive times 60 miles an hour. Okay, so we have our rate, we just need our time to plug in, and we can get a given amount of distance, and that's our function of time. Okay, so we're continuing to look at the graphs of functions and the usefulness of them. We're just actually working backwards here, where we're given the graph of a function, and we need to translate that. We need to derive the underlying function that's described in this graph. And there's a few ways to do it. Sometimes it's a little more intuitive, and sometimes you actually just have to plug in some points that lie on the graph and just compare them and see how they work out together. So we'll do some more examples with graphs in the future, so I'll see you soon.